Our first topic is closed loop simulation for autonomous driving and how to close the loop. Proof of concept of how set-level interface architecture can be integrated in third-party tools. We'll start with Marc Heinrich from the FZI Research Center for Information Technology. He is a model developer for the highly automated driving function, followed by Barbara Schuett, who is a researcher and PhD candidate, also working for the Research Center for Information Technology. And our third presenter is Riccardo Bartolozzi from Fraunhofer Institute for Structural Durability and System Reliability. And Riccardo is a researcher in numerical system and analysis groups. Marc, I would say the stage is yours.
Thank you. I also like to welcome you to the presentation about closed loop simulation for automated driving and how to close the loop. As said, the presentation is divided in two parts. The first part is about how it is possible to integrate multiple OZ interface models into a closed loop simulation outside of the simulation use case effort using a third-party tool. And in the second part, Riccardo will talk about how to close the loop and using modular concepts with motion control, actuators, and vehicle dynamics to take requirements into consideration. So for the first part, it is about how to integrate the OZ models with the set-level architecture into a closed-loop simulation. We're using a third-party tool. In our case, this is Carla Simulator. And it is meant as a proof of concept of the interface architecture developed in set-level, but is not meant as a complete test, so there is no traceability or credible simulation process involved. It's just about the integration. I'd like to start off by introducing you to the two modules we integrate. The first one is the highly automated driving function. It has three inputs. The first input is the driving goal in form of traffic command and OZ message, which is provided to the routing algorithm. We have object information, which is provided in the form of OZ sensor data that is provided to sensor fusion, and there's an object tracking and an object filtering module. And then lastly, there's odometry in the form of vehicle communication data, which is a OZ-like but set-level developed message, which is not yet standardized. Altogether, this goes into trajectory planning, and the output is a trajectory in the form of a motion command, yet another set-level developed OZ-like message. The hub function can be characterized as follows. We have an object list fusion, so no geometric fusion. We have an object tracking module, which tracks with constant velocity in a timeout. And we do react to road users according to their classification and also with regard to their relation to the ego vehicle and to the lanes they're on. The driving function is modeled on the intelligent driver model, and it has an extension for tight cornering to improve trajectory quality. The whole system is implemented in a modular distributed way based on ROS, Robot Operating System. So there is a converter layer which converts the input OZ messages to equivalent ROS messages and vice versa on the output side. The second module is a traffic agent. It also gets a traffic command from which a path is generated. It gets OZ sensor view, where it first extracts map data from, but also object data, which is then provided to object prediction and a maneuver selection module. And together with vehicle kinematics, we generate a traffic update. This is all based on a kinematic motion model. We have a rule-based object prediction, and the interaction with other road users is modeled at intersections. For example, we take indicator signals into account. The maneuver decision-making is based on game theory, and as shown in the previous slide, all interfaces comply with ASM OZ standard messages. Now I'd like to hand over to my colleague Barbara, who talks about the integration in Scala.
Thanks. For our proof of concept, we integrated both the head function and the traffic agent into the latest Scala release. We used OpenDrive map from milestone 1, which is a basic intersection, and we used Scala scenario runner for defining our scenario, what the agents have to do, which is based on behavior trees. For the integration, we used the Scala base agent, which is already used by Scala agents, and both the head function and the traffic agent, which is here called path following agent internally, implement this interface. On the scenario runner side, we implemented a new behavior for the traffic agent, and for the ego vehicle, we made a controller to use the head function as ego vehicle. And the setup is like this. We have a Scala Docker container where the server is running. We have the scenario runner, which is loading our intersection scenario that defines what the traffic agent has to do. It's communicating via OSI messages with the path following agent lib. And we have ego control agent as another client, which is telling the ego vehicle in the scenario what to do. And this ego control is communicating to another Docker container containing the head function, also via OSI messages. This is a video. What you're going to see is the head function is crossing the intersection, and the traffic agent is taking the right of way. The ego vehicle is braking and going on. Yes. We had a few problems and challenges. We had to synchronize all parties. As you saw, there are a few. And Scala has two modes, synchronous and asynchronous mode, which was making a few problems. Then also in Scala, the ego vehicle is not really defined by the scenario what the ego vehicle has to do. This is also the reason why we did not use open scenario in this case. And also, of course, we had to extract all needed information from Scala to put into the OSI messages. So this was just to show that it's possible to use a third-party tool with our set-level interface architecture. And we were able to integrate all our OSI models. However, we have to keep in mind that this was just a proof of concept, and this is a simplified closed loop, and it depends a bit on the use case, but usually we have more, or we need more sophisticated methods to close the loop after the head function, and this is what my colleague Riccardo from LBF will tell you about now.
So thank you very much, Barbara. So I will show my screen. So let me go a little bit more into detail about the motivation of the part 2 of this presentation. So how to close the loop for autonomous driving simulation. So what we need is a scalable solution for closing the loop with ego vehicle dynamics models in order to address different definitions of the system under test. And to do that, we need different model details, which depend basically on the system under test definition itself. So if we are considering models which are close to the system under test, we will need a higher modeling detail rather than if we are considering models which are far in the whole simulation chain from the system under test. What we have also taken into account are the test specifications, of course, in order to ensure that the different model with different details are always simulated within their validity ranges. And what we did and are still doing within the set level project is the implementation of such ego vehicle dynamics models in the whole simulation chain. And so with a closed interface with other set level components and partners, of course. And as we saw today in the morning, we are trying to support the simulation standards such as FMI and OSI in order to have a wide acceptance in the simulation community, including the conformity to the best practices in the industry and also the conformity to other current standards. So starting from the whole simulation environment architecture as shown in the simulation use case 2, what we are talking about now is the lower part of the loop. I talked just before about ego vehicle dynamics models. Actually, we are considering basically two model families here. One is the motion control and the other is vehicle dynamics and actuators. Both models here are meant to be delivered and integrated as functional mockup unit, thus supporting the standard FMI. and are connected to each other and to the rest of the simulation environment via OSI interfaces. Some of them are, as already pointed out, standard ASM OSI interfaces. Others are set level specific interfaces, which were developed and integrated in the current project. So the main challenge here was to complete the loop with this lower part, with the conformity to these standards, which are wide accepted, which have a big user community and are, of course, open source. So let's now go a little bit more into detail about vehicle dynamics and actuators. Actually, if we explode this view, we have several submodels within this block, and this is the current state of the work within set level project concerning the architecture of the vehicle dynamics and actuators part. So starting from the top of the picture, we have here the actuator management model, which receives from the motion control the target motion, let's say, as information, and controls the three actuators, which are in detail the powertrain, the brake system, and the steering system. All of them have an internal low-level control, and these three actuators basically drive the vehicle dynamics, which is shown here in the bottom part of the picture. So the vehicle dynamics includes the vehicle body, the suspensions, the tires, and eventually specific vehicle dynamic sensors. And we see at the end here of the picture, the vehicle dynamics block has finally interfaces as OSI message to the rest of the system, specifically to the world state and to the HID functions. And this is shown with a view once again at the top architectural level. So considering vehicle dynamics and actuators, we have these two interfaces as input. We have a ground truth message, which is basically an initialization message for the initial dynamic state of the system. And this is a standard ASM OSI message. And we have on the other side, coming from the motion control, the dynamics request message, which includes the vehicle dynamics target signals in form of longitudinal acceleration and curvature. And this is a specific set level developed message. Then considering the output side, we have a traffic update message, which is delivered to the world state, and which includes basically all signals concerning an update of the vehicle dynamic state, such as position, velocity, and also acceleration of the center of bounding box. And a similar content of the message we have in the vehicle communication data, which is provided by vehicle dynamics and actuators and delivered to the HID function. In this case, we are working within the project on a possible extension of the content of the signals, including some other information about the state of the vehicle dynamic model. And finally, concerning the models here taken into account, we have the final OSI interface, which is the motion command provided by the HID function and delivered to the motion control, which includes the current vehicle dynamic state and the target time-based trajectory. So this is how these interfaces are planned at the architectural level. And now I'd like to show you how we implemented them in simulation softwares which do not support natively OSI. So there is the need to support with this architecture also develop specific development environments for specific models, and a wide, let's say, employed software for modeling actuators or control systems, or even simplified vehicle dynamics model is MATLAB Simulink. So we addressed in this first half of the project the implementation of OSI interfaces within MATLAB Simulink, and with the goal to compile the model and deliver the model as a functional markup unit, thus supporting the standard FMI. So you can see here on the right side of the slide how we did that as a idea, as concept. So we have here a domain-specific system model, which receives as input domain-specific signals and delivers as output domain-specific output signals. And basically, we placed a so-called OSI wrapper, which is a function which is divided in two parts, so an OSI message reader and an OSI message writer, which actually translate specific domain-specific signals in standard OSI messages. And the goal here was to compile the combination of the model itself with this translating functions as a functional markup unit in order to deploy it integrated in the whole simulation environment. And to do that in MATLAB Simulink, we developed a C code-based function, which is then compiled as a MATLAB executable, so known as MEX file. this is how it looks like from the perspective of a Simulink user. So we have here a classical Simulink model as a subsystem, and we have here additional blocks which are on one side the OSI read function blocks and on the other side the OSI write functions. They are just at this level Simulink subsystems. If we look into detail at one of them, so the set level specific write vehicle communication data interface, we can see that from the model we have classic Simulink outports for the single signals which are delivered to this function block, which basically translates the signals to an OSI message, which is composed by the following classical three signals, so the base low, the base high, and the side signal. And so at the Simulink level, we have this combination of the model itself and this translate functions for the OSI message, and the whole system is then compiled, as I said before, as FMU. So after having had a look at the architecture and at the interfaces, I would like to show you some details about the models which are developed in the field of vehicle dynamics, actuators, and motion control. So specifically for the motion control, we have a model which is developed and provided by Fraunhofer LBF in the context of the set level project. And concerning the family, let's say, of vehicle dynamics and actuators models, we are addressing first several vehicle types, so car and truck. And we are considering two model details because, as I said before, depending on the system under test, we want to have the choice to switch between different model details. And so we have a model detail 1, which is a simplified single model for the whole system, vehicle dynamics and actuators. And we have a model detail 2, in which the single models of vehicle dynamics, steering, powertrain, brake, and actuator management are developed and delivered as standalone models and combined to each other following the architecture I just showed before. What we are still doing and concerning the models is a review of the conformity of such an architecture with a current ISO standard for the model classification in the field of vehicle dynamics. So for the demonstration we're going to show in the next slide, I would like briefly to introduce the models which have been used. So the first model is the vehicle dynamics and actuators in the simplified single model detail. As already pointed out during the use case 2 presentation, it is a 2D kinematical single track model with idealized actuators, which basically follows easily the target trajectory. And just in case some limits are reached, there is some deviations from the target trajectory. And these limits include the maximum values of grip, of motor, torque and power, of the steering angle and of the speed. So the use of the model is constrained to application of simplified approximation of vehicle dynamics in low acceleration ranges and where no 3D dynamics is relevant. That means no vertical motion, no pitch and roll of the vehicle. For detailed applications, we have developed and delivered a vehicle dynamics model of detail 2, which is a so-called reduced multi-body model. And depending on the suspension modeling, so we have a pure kinematic approach or an elastic kinematic approach. We have a variable degrees of freedom of the whole system between 14 and 34. And we are modeling here classically the sprung mass, the unsprung masses and the wheels, and implementing a Passeca handling tire model with additional vertical compliance. And so the usage of this model, as known in the field of vehicle dynamics, is related to such low frequencies applications like handling, and is not really suitable for higher frequencies applications like comfort or durability. Finally, we have another model involved in this demonstration, which is the motion control. It is a kind of non-linear state space controller as rear wheel feedback controller, which is based on a kinematic single track model. And it has 4 tunable controller parameters, one for each state which is under control. And the states are listed here are the longitudinal and lateral position, as well as the heating angle and the velocity. And this model includes within one model, let's say 2 versions, one for a low computational cost and the other one for a reduced deviation and better results quality. So coming up to the demo simulation, I want to show you, we set up here as let's say a small closed loop simulation involving just the motion control and the vehicle dynamics and actuators. And we have here as input a defined target time-based trajectory coming either from the HID function. And the motion control is meant to be the system under test in this demonstration. And what we wanted to highlight or to see here was the influence of the detail of the modeling of the vehicle dynamics, thus varying between the shown detail 1 and 2, just of the vehicle dynamics block within this model family. And all the simulation was implemented just in MATLAB Simulink at Fraunhofer LBF. And just to show one result example, here we have here an handling course, which is depicted here on the left side. And we simulated this handling course with 2 different velocity profiles. In one profile, we reached up to 0.2 g acceleration. And in a second profile, which addresses, let's say, middle-high acceleration ranges, we reached about 0.7 g. So both both velocity profiles are simulated with the 2 detail levels I showed you before. And so we have here, let's say in one slide, a summary of the results. We have here on the left side the longitudinal position deviation, and on the other side here the lateral position deviations, which are basically the errors between the actual and the target position of the vehicle on the track. And we see here basically how the model detail 1, which is based on this kinematical approach, shows almost no error due to the modeling detail itself. On the other side, we have more realistic deviations when employing the model detail 2. And we also see how these deviations are increasing when the simulation is pushed up to higher acceleration ranges, and so is much more different from an ideal kinematic simulation. And so that means also that in order to investigate and test and validate the motion controller, these examples show very well how a more detailed model is needed. So this brings me to the conclusions of this presentation. And in the first part, the FZI colleague showed this proof of concept, showing the possibility to implement and use the set level architecture and tools also outside the set level tools and other tools, integrating also different models and without requiring extra support. In the second part of the presentation, I just showed you how we, within the set level project, are implementing and implemented the models of motion control, vehicle dynamics, and actuators, and how we focused especially on the modeling detail of the vehicle dynamics part. And as next step of this whole demonstration, we could foresee the improvement of the shown proof of concept in order to address different system under test and to show the implementation of the different modeling details of vehicle dynamics and actuators. So thank you very much for your attention, and we are happy to answer your questions.
Thank you very much, all of you. I would like to hand over now to Julien Bou for the Q&A session.
Yes, thank you, Stephanie. So there are a few questions in the chat that came. I would like to start with the first one. So do you see, it's related to you presentation, Riccardo. Do you see possible extensions or modification of the current OSI interfaces with a specific focus regarding vehicle dynamics and actuators?
As I told before, we are working critically on that point. So many OSI interfaces which are currently developed or currently under review concerning vehicle dynamics are still under discussion also in the OSI community. So we have, let's say, 2 levels of investigation. On one side, we are close and we follow, of course, what happens within the ASAM OSI community, and on the other side, as already done in part, we are specifically developing, let's say, set level standards, which are meant to be discussed and hopefully integrated also in ASAM OSI in the future. So we see that it is, of course, for the second part of the project, an important, let's say, topic to work on and to extend and include possible other interesting and important signals.
Thank you very much, Riccardo. I think that answered the question.